take just a brief look at FPGAs, just to understand a little bit how some of the algorithms for synthesis may change if you use a different kind of target technology. Just a brief definition before we can talk about how the algorithms would change. These are field programmable, meaning that the hardware is customized by the designer. It is customized in the field as opposed to mask programmable, which means that it is customized at the foundry. What is this customization anyway? You start off with a blank wafer, irrespective of what the design is going to be, and then you go through a various set of steps determined by a mask in the foundry to customize that wafer into a functional chip. But here we are saying that this functionality is being customized at the site of the designer by the designer himself. That is what the field here means. It means that it is being done by the customer himself. This customization process is supposed to be at least relatively simple and cheap, and the FPGA chips themselves are produced in bulk. Of course, it is independent of the actual functionality to which the FPGA is going to be put, much like a processor that is produced in bulk and is independent of what software is going to run on the processor. Some very basic ideas about the internal architecture of an FPGA. Lots of things are programmable here. That logic block, will take a little bit deeper look into what it might consist of, but it can be programmed to do different things. That interconnect could be programmed to realize different connectivities, and finally, that IO pad could also be programmed into an input or output and so on. So, there is a lot of things that can be customized in there. So, ultimately you have a chip that can be customized to do very different things.
So, here programmability, we are not referring to the software settings which we do. Here we are referring to the logic connection.
Yes, the logic is being programmed, meaning that now it can do some piece of logic, but in a reprogrammable architecture, which is what these modern FPGAs are, you could change that function to something else. The hardware function is being changed to something else, as opposed to a processor in which the hardware is not changing. It is the memory into which the programmed instructions are being written, and we are reading those instructions and interpreting them in a hardware that is not changing. In the FPGA, the intention is that the hardware is changing. Whether it is changing at runtime is a different matter, but at least from one customization to the next customization, one use to the next use, it is changing.
Can it reconfigure at runtime?
Yes, this partial reconfigurability is a feature in modern FPGAs. You can do it. So, essentially what reconfigure means that the configurations also, it has to be dynamically accessible somehow. So, for some time you run it on one configuration, and in later stages you can run it on a different configuration. Modern FPGAs do have that facility. Yeah.
So, as I understand, FPGA is giving me a flexibility to kind of mimic multiple designs. So, the kind of RTL logic which it will carry will be much more than an ASIC. Let's say if I would have done an ASIC for a particular functionality, and I am doing a generic block. Okay, you can mimic this, you can mimic this, you can basically reprogram it to convert. So, on FPGA, if I realize my logic, let's say only subset of some logic is being used of the complete general logic, then our area, power and timing analysis equally good as would have been on the ASIC.
all the parameters will not be equally good. There is a price that we have to pay for the programmable hardware. That is obvious. That if you design an AND gate by hand, as opposed to some piece of logic which can be programmed to be an AND gate today or an OR gate tomorrow, then you have to give up something. You have to give up area because it is capable of doing multiple things. As compared to a customized AND gate, it would be more expensive. Similarly, there is an impact on timing, on power, on everything. Yes. So there is a price to pay
Then
for.
designers keep some tolerance that okay,
Yeah.
this can
Yeah.
be a kind.
So yeah, there is a price to pay, but it is a powerful additional feature that the hardware itself is programmable.
System bring up is really fast. So
Yes, it's as opposed to, for example, simulation. If you were to synthesize the same design into an FPGA just to do an emulation, the chip is not being sold as an FPGA, but the emulation is being done on the FPGA. That can be orders of magnitude faster than a simulation.
FPGAs would be a much powerful tool for testing and
Yeah. Yeah. So the emulation is that it's a much faster simulation. You could fix a lot of things. Functional bugs could be caught. It is not as fast, like we said, we are giving up on timing, so you will not get the same timing that your ultimately customized ASIC is giving you. Still, it isn't like 1,000 times slower. It may be only 10 times slower, 5 to 10 times slower. But that may be enough to do a much more comprehensive and extensive validation of your system before it goes into production. A lot of very powerful utilizations are there of the programmability feature.
So when exactly will people use, let's say, emulation on FPGA or a simulation in their design of chip?
People do both. Early stages you might do simulation, but it is very common that after you are fine with the simulation result, you might actually go for an FPGA implementation of the same thing. So that, for example, if you are designing a processor, you could actually bring up an operating system and applications and so on, because the speed permits you to do so. In a simulation, you are hopeless. Mostly, you can't do very serious applications that run for hours together in real time, which would become months if it is on the simulation.
Prototyping, higher abstract. So when we are
You want to be as close to the chip as possible. Higher abstraction you would always do, of course. So simulation does not go away. You would do all those abstractions even before, but you are going into more and more details of the design. So the simulation is getting more and more expensive. You would like to simulate everything. Your logic level netlist is being simulated, your layout is being simulated. There is limited amount of simulation you can do, but you would like to do that simulation. FPGAs do permit a lot more aggressive validation than you otherwise could afford.
and prerequisite for performing emulation is that I need to have my RTL logic ready. That also can be a differentiation for simulation. If I'm talking of higher
Yeah, ultimately this is an implementation. Where it comes in is you have, for example, if you are doing synthesis, you have done the synthesis. It is the last stage of the synthesis that is changing here. So you are much closer to the implementation here. But the advantage, of course, is that the design turnaround time is just a few hours, so you could do a lot of exploration, a lot of validation and so on using this kind of an architecture. Just to put up a high level picture of what a modern FPGA might look like. So what we saw in the previous picture was this and the IOs there, but there is a lot more in modern FPGA than this. The most of the area might still be occupied by this combinational logic block. They are the heart of the FPGA, they are what defines the FPGA, but there is the realization that by itself is not good enough for a number of other things that we would like to do. So, there usually would be some kind of a memory on chip memory that you would like to utilize, otherwise it might be too inefficient. If you have a lot of data, then while we will look at what the CLBs look like, they may at best carry some flip flops or something like that, nothing more complex than that. But you may want to store large amounts of data. So, what is called block RAM in the Xilinx terminology is usually there distributed throughout the chip for whatever use you want to put it to. There are DSP class of components, multipliers and adders. Those are important. When we say combinational logic block, we are essentially talking about discrete logic. Of course, you want to augment that with some powerful arithmetic components also. So, that discrete logic block might already have within it some adder logic at least, because it is so common. But multipliers are more expensive and they may be not necessarily part of that standard combinational logic block, they may be externally present, distributed again throughout the fabric. So, such stuff are there. If this you call one tile or a slice or whatever the terminology is, those are distributed all over the chip, so that you have arithmetic components close to your logic, you have memory also close to your logic. So, this part is what is the standard programmable logic, but the direction in which these FPGAs have evolved is that there are also some hard coded components, particularly processors, that are present inside the FPGA itself. The intention of programmable logic is of course very different as opposed to a processor that is programmable in a different sense. Here we want the hardware to be programmable, but it just turns out that systems that we design, even ASIC systems that we design, actually we would like to put processors into them, just because there may be parts of the system that are designed in software that would go into a processor implementation. Anyway, high level control might be performed in software and so on. A software component is usually there in any complex modern digital system. So, instead of leaving it to the designer to get a synthesizable processor from somewhere and implement it onto the programmable hardware, what FPGA architects have done is essentially they put some hard coded macros which are just processors. Okay, these look like standard processors. These are not programmable in the sense of hardware being programmable, right. So, this is a floating point unit, CPU pipeline, L1 cache, L2 cache, a scratch pad memory, standard controllers and peripherals and so on, memory controllers. So, these are what a typical processor environment looks like. So, but you might have a couple of processor cores or any number of processor cores embedded inside the FPGA fabric to help with all kinds of features. Essentially, if you want to implement a design in which part of the component is there in software, part of the component is there in hardware, then this kind of an architecture helps us implement that in a reasonable way. Most of the area might still be occupied by this programmable logic part though, but that software and the processor component is considered essential, at least high end FPGAs and FPGAs targeting SoCs would usually have some kind of processors. Of course, even if that hard coded processor was not there, there is nothing that is stopping us from synthesizing an FPGA down into these CLBs. You could do that, but as we know, there is a price to be paid. It won't be as good as a hard coded processor. Okay, so that's just the high level picture of an FPGA. All of that, of course, we will not be targeting in the synthesis course, but let's go down to the lowest level here and talk just just a little bit about how this programming is done. We ought to know that before we can synthesize into an FPGA. An SRAM is usually used as the programming element. This is just a normal SRAM cell which stores a 0 or a 1, and the programming essentially might translate to just writing a 0 or a 1 into that SRAM cell, but with a very definite purpose. This kind of programming that you do will have some implications. It may cause selections and connections and so on. That is what is essentially part of the customization of hardware. There is nothing fancy going on here, although this is only one kind of technology. There are other technologies that have been tried, programming technologies of hardware. There is, people have tried what is called an anti-fuse element, where if you pass a current that is above a certain threshold, then that fuse breaks, and that distinguishes a short from an open, for example. That is inherently how programming is done on such a design. Such a system may or may not be reprogrammable multiple number of times. The implementation as a memory, of course, has a nice feature that tomorrow you change that value to 0 and the meaning is something very different. Yeah.
But this typically when we compare this SRAM and DRAM, SRAM is like quite costly,
Yeah.
and then it will be a very bulky device if I realize a very big FPGA. Right?
Yes.
So did we ever, did researchers also try DRAMs and here? They would need to kind of refresh that, but that would be very small and very cheap because cost would be a challenge, right? Cost and area both.
DRAM cell I do not think has been tried out as a programming element, although you could have an on chip DRAM for storing your data. That is a different matter, and that certainly has been there. FPGA I am not sure, but certainly there are ASICs in which on chip embedded DRAMs have existed for a very long time now, but the purpose has always been storing of data because of its compactness, not really programming. Using it as a programming element probably has not been there because the SRAM is a faster device. DRAM is slower, it is compact, but it is slower. What is the DRAM anyway? It is a capacitor, right? But the SRAM cell, if you know, is a bigger cell. It is a 6 transistor circuit. While it is bigger, it does have the advantage of faster area. Also, we want this to be distributed all over the chip. It is not as though it is all there in one place. From that point of view also, some of the advantages of DRAM go away because the compactness arises out of a tight integration. If you distribute it everywhere, you may lose the advantage of density. Anyway, what kind of programming it is? It could be that you have such a selection kind of logic. There is one logic here, there is some other logic there, and this programming of that bit into 0 or a 1 might mean that Z has this kind of function or that kind of function. Of course, this is very elementary. For this you do not need any big support. You could write code that does exactly this. Point is that both X and Y had to be implemented, and it is not particularly novel. This looks like just a standard design. Other interesting applications are this. For example, the interconnection could be programmed in ways that you have two terminals that are connected by a transmission gate, and whether you write a 0 or a 1 essentially determines whether those two are shorted or not. That could be used to realize a programmable interconnect in the following way. You have some such design. This is a programmable box where you would like to establish any kind of connection, either this or maybe simultaneously this, or maybe you want some other kind of connection. Maybe you want this to be connected or that to be connected, and so on. So, many different connectivities could be theoretically possible. An interconnection fabric might actually look like this. So, while this box is there, you could realize any kind of connection. Maybe you do this and you just leave these two unconnected. So, that is the kind of programming that could be achieved by this kind of a structure. How would you do this? Essentially, between every pair of terminals that you would like to offer the programmability feature, either they are connected or not connected, essentially you would have maybe a kind of a transmission gate in which the control is determined by our memory cell. So, this kind of a thing is common in the interconnection part of an FPGA. If let us say I have, these are my logic blocks, and I want to establish a path between this, through this and this. Right. Maybe also simultaneously establish a path between this, this and this. All of this is okay. So, there is one programmable interconnect there that I need to program, which is decide whether that block is connected to that line or not. So, that is where that programmable interconnect is useful. But the more interesting interconnect is here, where I have these 4 things coming in and I decide which one is connected to which. So, all the pairs between which I would like to establish connections could possibly use that elementary programmable interconnect structure. So, how many such pairs are there? There are 6 pairs here, right. This could be one pair, that could be one pair, this could be one pair, this could be one pair, that could be one pair, and this could be one pair. Each of these you might want to connect or might not want to connect. Okay. And so, it is essentially 6 transistors that you need and 6 bits that control each of the gates of the transistors. The programmable interconnect would be just that. For one bit, if it is a bus that is coming in of 4 bits or whatever, the same structure has to be repeated 4 times. The logic block itself again consists of an SRAM based structure in the following way. So, what we have is just a piece of memory at the heart of the CLB. There is nothing fancier, it is just a memory piece. Yeah.
SRAM.
What will it retain the program after power down?
Not what?
Would have to reprogram.
Yeah, we would have to
FPGA and
go through just the programming. What is involved in the programming? There is a bit file that is the configuration file that we store elsewhere. So, when on power up, that configuration file has to be imported into the FPGA. It does not take too much time, considering how much time it remains on, that might not take too much time. But yes, if you power it down, then you have to read that configuration again before you continue. Okay. But the idea is actually very simple in this SRAM based FPGAs. Suppose I ask you to design a generic piece of logic that can implement any function of 2 bits. How would you do that? Any function of 2 bits means essentially I should be able to implement any truth table. A 2 input function with 1 output function essentially translates to a truth table in which there are 4 rows. Right. All of this is already known. The left side of the truth table is all known. So, what is remaining is this, essentially that one column is what is known. So, if when I say any function, what do I mean in terms of realization? You just need to give me a way to realize that column. So, you can see there is an application of a memory element like an SRAM.
It's kind of like a lookup table.
These are called lookup tables. Why? So, how would you perform it? If I gave you some memory and asked you to build any function of 2 inputs, 2 bits, how would you do that?
You
Yeah. So, that column there just needs to be stored in the SRAM, that is all, and that input here just is the address. The whole thing is just a combinational logic. It's realized using sequential elements, using memory elements, but there is nothing fancy here. It's just the AB, that is the 2-bit address to the SRAM structure, just corresponds to whatever is the input. In the corresponding location, we store the appropriate bit, whatever that truth table says.
You don't use any gate level implementation on the FPGA for such logics.
This is one way of doing it, but actually this is what is the prevalent
Because sir,
way.
in the softwares, like when we try to see that elaborated design part, it gives us the gate level implementation of various gates. That's how the tool is implementing the logic.
But that is still a little higher level. What is there inside the combinational logic block is not exposed to you. You don't see that, yeah. Yeah, but we will get to what the steps are. But that is still a little abstract view. If it is showing a netlist to you, that is a little abstract, right. What is there inside, particularly how this translation is made to what is there inside, is proprietary information that will not be visible to the user.
Sir, it's not like that gates are already implemented on the FPGA and we burn the inputs according to the program.
The burning means writing into those SRAM cells.
Writing in the SRAMs, we are not writing at the input of the logic gates.
But why don't we see a little more complex example? But at the heart, it is this idea is this. The lookup table, why is it called lookup table? It is because much of the implementation is through a lookup. Like there is a little bit of logic also. There are some flip flops also. Separate flip flops. These are also memory elements, but some D flip flops might also be there as part of the.
These memory elements, we are just storing the input at the start of the program, and no matter how a program succeeds, these values will retain as it is.
Yes. Also, that is one part of the FPGA's memory, which is a configuration memory. This memory is not visible to the programmer, to the designer. In our picture there, that block RAM is what is available to us for storing data and retrieving data. The block RAM structure we can control. A configuration memory I did not really show in this picture. It has to be embedded as part of the CLBs somewhere, but we do not get to see that. Modern Xilinx Vertex 7 kind of series architecture looks conceptually pretty much like this. Like if you extend that 2 input argument to a 6 input argument, what do you need there in that lookup table? What is this structure? 64. It is 64 bits in the structure, that is all. Given that, you can implement any function of 6 inputs. While that is the basic idea, of course, people are always working on tweaking and improving that lookup table structure and that CLB structure. So, there are a few other things that are useful, and the FPGA designer would make those things also be part of the CLB structure. We said that there is a need for storing data. That storing data does not actually form part of the CLB. You would have to store data in block RAMs if you wanted to do that, but there are some flip flops that they would include in addition to these LUT structures that are used for combinational logic only. Okay, so 2 things. One is flip flops would be there. Other is some adder kind of circuits would be there because they are very useful. What they might give is maybe a 4-bit adder and expect you to realize a larger adder by chaining multiple 4-bit adders that are spread across different CLBs. So, this is used for discrete logic. You just have some random Boolean function, you would implement it using the LUT, but there are a few other things you may want flip flops output, you may want to register for some reason, and they may give some flip flops there, but they might also give some adder bits, either 2 bits of an adder or 4 bits of a simple carry chain that might be there. The way you would implement a bigger adder, wider adder is that you make sure that the carry chain is appropriately set up. Output from one CLB goes into the appropriate input of the next CLB. But here too there is a little bit of variation that you can think of. What if instead of a function of 6 inputs, you want to realize 2 functions of 5 inputs each? 6 inputs may be the most general structure, but it could be that often I do not have 6 variables, maybe I have only 3 variables, but I still want an efficient implementation. You can see that if your functions were all of Boolean functions were of 4 variables each, then the 6 input LUT is sort of an overkill. Of course, the larger that number of inputs is, the more the delay is of this structure, and the more the area is, and so on. But can we think of a simple variation? Imagine what that 6 input LUT looks like. This is just a simple memory structure, nothing more than that. But what if I wanted instead 2 functions of 5 inputs each? Idea is I should be able to reuse that structure sometimes to perform any function of 6 inputs, but at other times to perform maybe 2 functions of 5 inputs each, or maybe there are thousands of these elements spread over the FPGA. Some of them I can personalize as one Boolean function of 6 inputs, but some other of those blocks could be customized as 2 Boolean functions of 5 inputs each. 2's complement. How many bits are needed in an LUT which is 5 input? How much storage is needed? It is the size of the truth table, 32 bits. So, this one requires 64.
Bit can be alternatively used for 2 different functions.
Right. So, one idea that suggests itself is let me divide this into 32, make these the same size. Instead of having one 64, let me have 2 32. That at least is the heart of the logic, and that should not be hard to do. But in addition, I can do just a little bit. So, there are 6 inputs here. Now, this one takes 5, this one takes 5. What else?
Sixth one is deciding if it is this one or this one.
Selection line to a mux can be the
So, the outputs of these can go to a mux, in which we say it is that 6th bit, 6th input could actually select between 1 or 2. What about the connections here? These were my A1, A2 and A6. So, here what are the connections?
A1 to A5 are common to the both 32-bit inputs.
Right. So, that structure is actually very simple, it is just this. What it is showing is that output O1 is which? This is the normal 6 input function, right. So, that is the 6th bit, and these are my 5 bits, and I have some such structure like that, and this is my 6 function. Any function of 6 inputs, I can spread it over the 32 bits that are here, and I could choose one or the other depending on
But now 30 addresses are kind of not used, right? So
what?
so first 5 bits.
This is 32 and that is 32, right? This is 32 bits and this 32 bits.
But the addresses will be a contiguous address, right?
If I keep the same bit logic there, then my address selection, the memory is contiguous, the LUT table. It can't be.
Right.
That's why I said 2's
What was our
complement.
truth table? Our truth table was A1 through A6, say, and I am saying I have O1 as the output, and these correspond to our A6 being 0, these correspond to A6 being 1, and whatever was there, that is what goes into that LUT, and these elements go into this LUT. This is a standard way. It is just that what would have otherwise been part of that decoder is now explicitly done as a mux. What about the other output, O2? O1 is the output of the mode where I am using this logic as a 6 input, right. But I could also be using that logic as 2 functions of 5 inputs each. So, that means that this is one function, that is a totally different function, and that is when the O2 is relevant. Otherwise, in the other mode the O2 is not relevant, and this one anyway can be selected here. This is not selected, right. And that A6 can be used as a selector.
In a typical CLB, I have not seen one, but I was guessing that if I have
a 64-bit LUT, all my decoder for memory is sitting before the memory, not after the memory. But in this case, we are saying that either we have rerouted or something, but within the CLB itself, I could shift that decoder, that is the last decoder of A6, the MSB, after my memory, which is counterintuitive to me because the hardware is fixed in most cases.
Oh, no, this is what the hardware looks like. This isn't a theoretical one, this is taken from the Xilinx hardware. This is exposed
this is how they implement the CLB.
Right.
Okay.
This is the CLB, for the reason that most of the time your functions may not be very general, sometimes you need smaller functions, right. So, this is more efficient, otherwise you would need another CLB for the smaller function, which may be wasting area. You could think of other variations, Y2 you can have 4 different and so on, but that is what the current CLB looks like, but that is what the Xilinx CLBs have always looked like. The size has been changing over the years, they started with maybe 3 to 4 to 5 and so on, but the philosophy has been this only all the time. Their difference in the way they have evolved has been in what other components they are putting there, maybe they had a few flip flops. So, some of that also has been changing, that number has been changing, but the evolution is really more along the peripheries and putting processor and such things to make it more attractive for proper system designs than the CLB itself, which has looked like this conceptually forever.
So, if this is fine when we have a 6 input LUT as an input and we want to implement 2 5 input functions.
Right.
We can similarly have a criteria for 3 input functions also, 2 input functions also. So, the question is that do we have only this, that we have 5 input LUT fixed and 1 mux outside, or inside that 5 input LUT also there is a mux encoded according to that?
See, somewhere there is a trade off between efficiency of implementation of the CLB. There will be tens of thousands of these CLBs. So, while it is okay to have a very general structure, you are paying a price in terms of area all the time. So, this was arrived at statistically, there is no theoretical reason why it should be just this, but it is just that you have a large number of functions to implement. They have various characteristics with respect to how many inputs they are. Sometimes they are 2 and 3 inputs, in which case this is an overkill. Sometimes they have 10 inputs or something like that, and then you have to use many instances of these CLBs to realize them. The 5 and 6, these have been arrived at by looking at the statistics of the way these things are distributed. So, indeed if you have very small functions of only 2 or 3 inputs, you are wasting some space. You do need a CLB. So, it is not a general structure, it is this kind of a structure usually where you have only 2 functions, not any number of functions.
So, this structure we arrived after we had a 6 input LUT and we looked inside it, so we saw this structure. That is true, right?
No, say again.
We were looking at a logic block of a simple 6 input LUT.
Right.
So when we looked inside how that is implemented, we saw this structure.
See, a 6 input LUT otherwise wouldn't be implemented this way. Right, it would be implemented with a standard decoder and one SRAM that is a lot more efficient. If you put muxes there, then the area increases. This is what the CLB, the selected CLB by Xilinx is, that you do not have to do it that way, but this is what that structure
If
is.
we again look inside the 5 input LED that is visible here, will we again see such
No,
structure?
no, you will see a memory structure, standard memory structure. But in your FPGA you could do it that way, that you could split it instead of the 5 input. There is nothing sacrosanct about the 5 number, of course. You could split it further and instead have 4 different 4 input tables if you would like to. That is a designer's choice and a trade off. But it fundamentally impacts our synthesis algorithms because they have to be aware of this structure. It is not as though you can have 4 functions of 4 inputs each. You can only have 2 functions of 5 inputs each for this kind of a CLB structure. So, when we say that this is my general logic and you synthesize it with that FPGA as the target, that tool has to be aware of this internal representation.
They can combine smaller components into bigger with
Aligning all the inputs and making it 6 input or 5 input.
Smaller components could be combined into bigger ones. For example, if they occur in sequence, output of one is going as input to the other, then the whole thing might form a different function of maybe 4 inputs or 5 inputs, but still fit within one of these. That is the intention of this kind of a design, that often you can pack smaller logic into others. But if you need the independent outputs of each of them, then this does not work. This limits the number of outputs that are there. With that kind of a logic structure, how would logic optimization work? First of all, we have 2 phases, right, in the multi-level logic minimization. There is nothing particularly 2-level about this. This whole thing is that you can take output from one of these CLBs and you can take it to a different CLBs. It is in a very natural way amenable to multi-level logic implementation. So, multi-level logic implementation is done in 2 phases. We had that first technology independent logic optimization phase, and then there is a technology dependent phase. Often it might be that a technology independent phase is not different at all, it is the same. There we are minimizing literals or whatever we are doing, we do it the same way, there is nothing different, but that second phase would be very different because the realization is different, the technology is different, the target is different, you want to optimize for this kind of a target. Now, what is the library? In that tech map phase, there were 2 inputs. One was the netlist, the generic netlist, but the other input was the library. Here, what is the library? The library had a bunch of standard cells if it was a standard cell implementation. All the cells were enumerated there. Here, what is the equivalent? LUT is the equivalent. How do I incorporate it as part of my tech map? D flip flops are fine. Yeah, they are there just like they were there as cells in the standard cell library, and in fact we have embedded some D flip flops in each of these CLBs. So that is fine. So, just the logic itself, the logic there was implemented in terms of standard cell library elements. Here they are LUTs, but remember the way we were doing the tech map there is a series of steps where first we did a decomposition into inverters and NAND gates. And then there was a mapping of that structure, and there was a particular matching and covering strategy that we had. What would the equivalent here be? First of all, LUTs are library elements, but how do I go about the matching? In fact, there we had decomposed a more complex netlist into simpler elements, primarily because the matching becomes easier. Right. Here, what does matching mean? That LUT can be programmed to be any function. Therefore,
No matching required, just the number of
matching
inputs.
is trivial. Whatever I have can be matched.
Right.
It's a matter of me customizing that LUT to be whatever I want it to be. So, there is no real matching to be done here. Is there any covering to be done?
Covering.
If we do neither matching nor covering, then there is nothing to do in that technology matching phase.
at least the reuse one has to look at. If
First of all, since any function can be implemented, there is nothing to do with respect to matching. Actually, even in the other case, we had simplified the matching by just saying that we just look at how many inputs are there. There is only one gate which is a 2 input NAND gate. I just have to make sure that the number of inputs match, just like I did there. Here also, that is all that I need to make sure. Now, covering actually is not really complicated. You treat that library cell as a black box with some number of inputs. If that LUT has 5 inputs and 1 output, it can be programmed to be any function of 5 inputs and 1 output. We are just looking at a black box with 5 inputs and 1 output, whatever it is. And there is no need for us to decompose into NAND, inverter and so on, because I know that any function of 5 inputs or 4 inputs can be realized. So, the technology mapping just consists of covering that network, which is that subject graph, in terms of subgraphs of 4 to 1. What logic is there inside that structure is not important, because I know I can realize it anyway, right, with an appropriate configuration of that LUT. So, the only thing that I want to do here is cover the entire network by subgraphs of that property, that it should have 4 inputs and 1 output. Maybe I want to minimize the number of such boxes in terms of which I realize the logic. If it is timing that I want to optimize, then it would be the depth of that network that I realize it in terms of, that is what I would like to minimize. So, this is all I wanted to indicate that would be a variation for technology mapping. There is the other issue that I have a fixed number of functions in each of the CLBs and so on. So, other complications are there, but the principle is just this. What changes from the standard logic optimization procedure? It is just this. In fact, it looks like it is a simpler problem for us. But what does complicate it is that the CLB is not just this, there are a few other things, there are arithmetic logic and so on. So, there are other things to be done, and overall the synthesis process is indeed complicated, but some of the elementary processes are simple variations.
The interconnection is the difficult one, right?
Yeah, we did not talk too much about timing, for instance, here, and the timing is influenced by the route that the wires take. While this step itself might not be too complex, the place and route is a complex process that does influence timing in other technologies as also in FPGA. We will conclude the synthesis discussion with a couple of adjacent topics that can't be completely divorced from synthesis. We have been talking about timing in various forms. That is why I thought there is a need to look at some of the very basics of timing analysis. The algorithms are all variations of things that we already know, but this topic by itself is a complicated one. It deserves a course on its own. Really, there is no way to do justice in the 2 hours that remain, but there is an interplay of some of these topics with what goes on in synthesis. That is why this is included. Okay. What are we trying to do? We are trying to statically compute the delay first of just a combinational circuit. The delay is the worst case, irrespective of what data you give on its input, you say that this is the worst delay. Why is this useful? Of course, it is of fundamental importance. If I know that the delay does not exceed a certain amount, then I can use a clock period of that duration to run the circuit. Of course, the job of synthesis is to make sure that that delay is as small as possible, but there would be a different analysis engine that at the end of the synthesis you could run and say that this is the delay. Why can't I just simulate it? Simulation, a gate level simulation does tell us what is the delay. If you set the input, the changes at the inputs of the gates will propagate to the changes in the outputs, and when you see that the output has stabilized, that is how much time the logic has taken. So, I could use this as an alternative or not. So, simulation requires what other input than the netlist itself. Synthesis has just that netlist or whatever is your function specification, that is what it has.
Constraints.
Constraints, can't you impose constraints on synthesis tools? Constraints are there, those are input. We have used constraints as part of all our synthesis algorithms. You can't say at the end of the synthesis course that I don't know about constraints. We do impose. When it's a resource constraint, that's a constraint. Deadline is a constraint. But simulation has one other input. The input vector, the input vectors are provided. The simulator does not run without you saying what is the data on the inputs. To the synthesis tool, do you say what is the data? You don't. The point of timing analysis or static timing analysis is to compute that delay without taking any data. At least in a purer form, it would not rely on information about whether the particular input pin is 0 or 1. The result that it gives is a powerful one in that it covers any input that you might give. Simulation would cover only those inputs that you actually provide. So, a quick differentiation could be made between these two mechanisms. Both of them could be used to validate timing, but if I do a simulation versus timing analysis, there is one thing about accuracy that maybe we get back to later. We are saying that simulation could be more accurate than timing analysis. Without knowing what is timing analysis, it is hard to resolve that, but all the others should be clearer. Simulation actually does a lot more than just the timing. It does functional verification, right? You look at the logic output and decide whether it's working or not. Functionality is working or not. Timing analysis has no such feature. It only tells you timing. Everything may be wrong, but your critical path might look good. It actually might be a very fast circuit that does something that is not required. Coverage. We say limited coverage versus high coverage. What do we mean? You need to provide input vectors for the simulation to work, and of course, we are limited by how extensively we can generate those vectors, how comprehensively we can simulate the circuit with the vectors, just because there are way too many vectors to test it for. But in the timing analysis, the coverage could be much better because you are making a strong statement that irrespective of what the data is, your circuit has only so much delay. Because of the same reason, there is a speed difference. Simulation is relatively slower, but timing analysis could be fast. Capacity, again we are limited by capacity just because of this. These are all related to each other. All these four are related to each other. Let us get on to a very simple timing model using which we can illustrate some things. Let us assume that the gate delay is 1 unit. Let us assume that we have the same gate delay from all the input pins. We are just indicating generalizations that later need to be done, that is all. The reality is that that delay might be different in general from this delay. Right? From delay means an input changes and how much time later the output changes. It depends on what the circuit is doing. The result of one input changing might propagate much faster to the output than some other input changing in general, of course. Same delay for both low to high transitions and high to low transitions, that too need not be the case in general. Same delay across all the loads, that of course is not true in general. There is no wire delay. So, lots of things are simplified here just so that we can put up the most basic algorithm. And the other thing is all the inputs are ready at a particular time, time equal to 0. That also might not be true in general. If it is not true, then you could exploit that to perform a more aggressive timing analysis. Okay. This analysis is with a graph in which I need to define only two things, what are nodes and what are edges. But the way we are treating this problem is that the nodes are the nets and the edges are the gates. So, why do I have that edge between A and E? That edge refers to the gate, and there is a node corresponding to A, there is a node corresponding to E. Okay. So, E to D, there is an edge because of the same reason. So, that is my, and this is not done just to do something different, but it is useful in some ways. So, that is why the model is done in this way. There are delays associated with the nodes. As of now, we just said it is 1, but in general I can put any delay there, and that can be included in some appropriate way. A trivial levelizing algorithm is something that we can start with. Let us just assign levels. Levels are useful because they tell us when a signal arrives at some inputs or some output. This is a DAG kind of a circuit anyway, so I should be able to assign these levels. So, all of these that do not have any inputs I can pick up, and that is my first level, level 0. All the others that have inputs from what is there at level 0 can be put into level 1. So, that is how level 2 would be defined, 3, 4 and so on. This, as you can see, is very similar to that ASAP scheduling algorithm. Algorithm is very obvious. You just say that while all the nodes are not labeled, you consider the nodes one at a time, and if all its predecessors have been labeled, then you are able to label this. What label will you give it? It would be 1 plus whatever is the max level of any of its predecessors. That is all right. The level is just an estimate of the signal arrival time. All the input signals are arriving at time 0, then these signals are ready at the end of time 0. For C, the inputs arrive at the end of time 1. For D, you have all the inputs, well, when I say inputs arrive, all the inputs are ready at time 0. That is what the.
So here assumption is that all the paths have same delay, right?
No.
Otherwise
Paths are different. Oh, we are saying that at that time all the inputs are ready. So, for D you can see that one of its inputs got ready earlier. Okay. It is this one that arrived later. The computation of D essentially starts after all its inputs are there. So, timing analysis of this circuit means that you are finding what is the maximum level of this circuit. Having done that level analysis first, then you could determine what is the critical path of this circuit. Critical delay is that level number itself. Critical path, we may be interested in what would be the point of knowing about the critical path, having already known the critical delay. The critical delay tells us at what clock I can run this circuit. The path, why is the path useful?
We can retime it if necessary.
It helps in identifying any bottlenecks that are there. That if it is not good enough, that is where we should focus. Right? Maybe I can do something about it. So, what is that critical path? It is the longest delay from any input to any output. That is what the longest such path would determine the level anyway. Modulo that path being sensitizable in ways that we will look at later. For now, it is just a structural computation. The path could be easily obtained by just backtracking from the output. If this is the level, you just proceed to that input, corresponding to the maximum arrival time. So, you would pick that, go back from here, you would pick this, from here you would pick this, from here you would pick this. That is the path that we are interested in. Recursively, you visit the predecessor with the highest level. So, this is a simple computation. We can very easily relax the assumptions that we started off width. Our nets and gates still are our nodes and edges, but the gate delay need not be unit. I can make it whatever I want. Instead of 1, I can say it is 3 and 2 and so on, and I can represent that in my graph here with a corresponding edge weight. The earlier model I just had an edge, I did not have weights on the edge, but it could capture the delay. The delay of the gate, remember the edge represents the gate. Okay. Now, I can compute the signal arrival times using just a variation of that same algorithm, where I was calculating level plus 1. Instead of level plus 1, you would just take that edge weight whatever is there and you would appropriately set it. So, that is fine as far as the computation of the level is concerned. There are a number of other adjustments that we could make, number of other features that we can capture in this formalism. I could have different pin to pin delays within a gate, right. In general, I have such a structure. That delay may be in general different from this delay. It depends on what that circuit is doing. This is just a block, right. Inside that block there may be other things that are happening. If you look at the transistor diagram, you will find that some paths are faster, some paths are slower. Can I incorporate that in our representation?
Yes.
Yeah. Each of these are nodes, right. Right. So, I have 3 nodes, and earlier this was my graph. How can I change that? To represent the fact that these delays are different. So, earlier we used a fixed gate delay there. So, that same delay would be annotated on both of them. If those delays are instead different like that, then I could have something like this. I could use the same structure to find other answers like the earliest arrival time. Instead of latest arrival time, I can say earliest with just a small change. You use the min instead of the max. So, you could do a lot of things. Instead of the max delay path, you can find the shortest path by doing the appropriate backtracking using the minimum arrival time instead of max. If you had a non-zero arrival time at the primary inputs, that was also one of the assumptions. We said that all primary inputs are available at time 0. If it is non-zero, then how would you adjust this? Actually, the way we have designed this graph, there is a placeholder already. These represent the inputs, right. So, we can put numbers there also, or instead of this being 0, this can be something else, and the rest of the graph does not change. So, much of this can be done. Of course, the problem with timing analysis is that it is not as simple as this. We have already alluded to this in other discussions. In general, there are other dependencies. It is not constant, right. If it is constant, then it is fine. We could use all of these strategies, but reality is that there is a more complex function. For example, it is a function of the output load. So, there are other dependencies. There is a function of the input slew, the rate at which the input is changing, that too is determining the load. So, all of this does need to be taken into account there, but I am just pointing out some very simple extensions using the same formalism, nothing different. We could also discuss in this context a required arrival time for a signal. So, the earliest time when a signal is required to arrive at a node, that you just start at the output node. Instead of just computing the delay, let us say you want to find some bottlenecks or something like that. You want to say if that is the max delay that I can afford, then what is the required arrival time at each of the inputs of the gates. You start at the output node and you traverse that delay graph backwards, you can annotate the required time. Instead of propagating from 0 and from the inputs towards the outputs, you could also do the reverse. Okay. In the process, you could compute what is called a slack, which is the difference between the earliest required arrival time and the latest arrival time at the input of a gate, say. That slack indicates the sensitivity of a circuit to a signal, in the sense that if that slack is positive, that is required arrival time is something, but the latest arrival time according to the circuit that you have designed and according to the numbers that we have for the gates is something that is less than the required arrival time, that means that there is a positive slack at that node. At that node means at that net that corresponds to that node. That signal that is there at the node could be delayed a little bit without affecting the critical path of the circuit. Okay, so there is a gap, it means that this is a good situation to be in, or at least it is a situation where we are not too much concerned about that particular node, because we have our signal at the right time. Okay. In fact, it is before what we actually need. So, if a slack is positive, it means that that signal as of now we are not worried about that particular net and signals going on that net. If that slack is 0, then that node is on the critical path. If it gets delayed a little bit, then that delay will propagate all the way to the output. If it is negative, it means that that signal will not meet the timing requirement. Okay, it will arrive too late. What does that tell us? So, that is important information, we have to do something about it. There is some speed up, some acceleration that is needed as of now, because we are not meeting the required timing.
So would it help if we look at
Slack at each node in the path, because if I
this is defined at every node of the circuit.
if an intermediate node itself
we are not able to meet the slack, that means the subsequent will not be able to
Yeah.
recover in any
Yeah.
case.
So, that slack will be 0 for all nodes of the critical path, if it is 0 for one node. There are some things that complicate the timing analysis computation. This should be expected. If it was that simple, then it would not be a valid subject of analysis and discussion here. This has to do with a very interesting phenomenon called false paths. Consider this circuit. The longest path according to just the structural computation is this, right? It is this. So, while it seems fine, the question is, can this path be sensitized? So, for example, if you run a simulation with data, will you actually get that delay or not? You keep other inputs constant. Okay. Delay of course means that if that is my critical path, then I should be able to recreate a situation where the rest of the circuit is constant, and because of a change in that input, there is a change that is reflected at the output after a certain time, and that time hopefully should be 1 plus 1 plus 3 plus 3 if that is the critical path. Do you think that is possible for this circuit?
or followed by the and is
Where the limitation is G will not be, so the B has to be, the B bar has to be 1 at the same time. For
Right.
OR to function it has to be 0, so it can't be true, so that's why G cannot be. So
Yeah,
B
there is some analysis. This is not merely a structural analysis. There is problem is it depends on what that gate is doing, and depending on what it is doing, a path that seems structurally as though it is a critical path might not actually be sensitive. This is what we mean by a sensitizable path. So, the issue is the following. Suppose B goes from 0 to 1. But if you look at B going from 0 to 1, then that goes from 1 to 0. Because this went from 1 to 0, that output 10 to 0, 3 later. Basically at time 4 F got set. Remember, this is irrespective of the fact that something happened at A or did not happen at A. Right. So, it is that path that got sensitized really, if the transition on B was 0 to 1. So, the A has no impact, input transition at A has no impact. What if it was the other way around, B changed from 1 to 0, then D changed from 0 to 1, which immediately caused G to change irrespective of anything that happened there. Okay. Either way, the transition in A was not really dominating this computation of the critical path. So, this longest path that we had identified structurally is a false path, because it can actually not be sensitized. So, the critical path actually is this in this circuit.
So by sensitized, we mean that it cannot be evaluated as in the critical
Signal
path.
flow.
Right. So, you should be able to control the situation in a way that you hold the rest of the circuit stable, and a change in the input should reflect in a change at the output. Right, that is sensitization. We will get to a clearer definition of sensitization. Informally, this is what it is. Okay, so let us suspend it here.